We've already looked at properties of solids and behaviors of solids, and today we're going to look deeper at properties of fluids. So fluids are anything that flows, so they don't have a definite shape, but they may have a definite volume. So gases don't have a definite volume. That changes depending on the container that you're in. Liquids do tend to have a definite volume. So anything that flows is considered a fluid, so gases and liquids. One of the first things we're going to talk about is pressure. When we apply a force to the surface of a fluid, we exert pressure on it. And that force is usually perpendicular to the area, the surface area of that, whether we're talking like a gas in a tank or whether we're talking about liquid in a cup. If we apply pressure, then we put a force on it, on the area. Now, we measure pressure in pascals, which is 1 Newton of force per square meter, but that's a very small amount of force. So usually you're going to see kPa or kilopascals as our force measurement. And the name comes from the guy, Pascal, and his principle that the shape of the container has no effect on the pressure at any given depth of this fluid. So here we have a device that has containers that they're all connected throughout. It's almost like a multi-branched test tube, right? And they have different shapes and different sizes. And if you notice at the top, the water line is at the same level on all 4 of these branches. No matter where we take a pressure reading, whether it's here or here or here or here, it should be the same pressure because any change in pressure is transmitted throughout the entire fluid. So if we put pressure on this one right here, that pressure will be distributed throughout the entire thing, and the water will kind of squirt out the other 3 where they're allowed to move. So squeezing something or applying pressure distributes that pressure throughout the entire fluid. So think about toothpaste in the morning. Some of you have the method of squeezing your toothpaste from the top, like right next to the cap. Some of you squeeze it from the middle and some of you roll it up from the end, right? There's no wrong way to squeeze a tube of toothpaste because no matter where you squeeze it, you could just put the thing on the counter and karate chop it, right? It's going to come out the end. So that has to do with Pascal's principle. No matter where you squeeze it from, that fluid pressure inside your tube of toothpaste is evenly distributed and the toothpaste will come out the cap. The same idea goes with hydraulic lifts. We use hydraulics in car lots, like trying to raise up cars to work on underneath, like where you get your oil changed. Those barber chairs that they step on and you can hear the air pumping through it, that's a hydraulic chair. You apply a force to a small area, bigger force, small area, and then that force is distributed over a larger area. So you can lift up heavy things by using this distributed fluid pressure down in the bottom. All right, so fluids exert a pressure on their surroundings, just like the surroundings exert a pressure on them. When we put an object in a fluid, such as we've put this block of wood here in this cup of water, the fluid exerts a force on the block of wood. Now, if that upward force, what we call buoyant force, is greater than the downward force of gravity pulling on the object, then the object will float. If the fluid pressure, the buoyant force, is less than the weight of the object, such as in the second picture here with the steel, then the object will sink. So playing the sink or float game has to do with that buoyant pressure. The force that your fluid puts on your object. If you want a steel boat to float, you obviously don't make it into the shape of a block there. You have to take up a greater space, allowing the pressure to push on it more, and so that buoyant force becomes greater than the weight force. Big, heavy cruise ships can float because they're gigantic in size. The more fluid that is displaced, and that's Archimedes' principle, the more fluid that is displaced, the more force you have pushing on your object. So the magnitude of that buoyant force, how much buoyant force you get, is equal to the weight of the fluid that is displaced. So it's easier to float on things that are more dense, that are thicker fluids. So like There's pictures of the Dead Sea where people float in the Dead Sea, whereas they have trouble floating in swimming pools. The Dead Sea is very, very salty, so it's way more dense. The fluid that is displaced by somebody would weigh more than the fluid that's displaced by somebody in just a swimming pool with regular water, right? So you're able to float because you have more buoyant force. Swim bladders in fish work by the same principle. The fish takes in water, which expands the size of the fish, and that lets the fish move up in the water. Whenever they want to go down in the water, then they expel that water out of their swim bladder and move down. So that is Archimedes' principle. Now I've got a video here for you about how Archimedes' principle was discovered by Archimedes. So go watch that video and then come back. All right, so we've talked about how boats float. Now let's look at how planes fly. Well, it's very tempting to think that it's just a whole bunch of magic, right? But don't worry, it's not magic, and it won't suddenly stop in the middle of the flight that you've got. It all has to do with Bernoulli's principle. Now, Bernoulli was a guy that figured out that as the velocity of a fluid increases, so when the fluid is flowing, the faster it goes, the less pressure it exerts on its surroundings. So here we've got the wing of an airplane, and the airplane is moving. So we've got air moving around the wing of the airplane because it's going through the air. On the bottom of the wing, your air doesn't have to go as fast to get from one side to the other as it does on the top. You notice the top is rounded, so it's got further to go to get from here to here. So since it has further to go, it has to move faster. Faster air exerts less pressure. Less pressure on top, more pressure on bottom creates that lift that lifts the plane into the air. So here we've got almost like a garden hose, imagine if you will. There is water or a fluid coming through. As that pressure increases from the outside, your velocity has to go faster. So the same works in both regards. As your velocity increases, there's less pressure on the outside. If you increase that pressure, then the velocity has to increase. That's why whenever you stick your thumb over the end of a garden hose, it squirts out a lot faster. So I've got two little videos with do-it-yourself activities. You can try these at home. We'll do some of them when we do our labs together, but take a look at these and see if you can see Bernoulli's principle at work. All right, so when we look on a molecular level at the behavior of fluids, we get some forces happening between our molecules. One is cohesive forces. Now, think together, like a co-ed team, you're working together. Cohesive forces, they're trying to hold each other together. So cohesion holds the particles of a fluid together with each other. So you can see in the picture right here, there's molecules, there's forces in between all these molecules that hold them together. A special type of cohesive force is the cohesive force between the molecules that are on top. I'm going to go back real quick. If you see on the top, these molecules are attracted to each other side to side and to the ones down below, but there's nothing above. So all that force gets concentrated on that top, that surface, and it creates almost like a skin. The surface of the liquid holds together so tightly that it contracts to the smallest possible area because you've got those attraction to the side and down, but there's nothing above to hold on to. So this is a water walker. It's a little bug that lives in an aquatic environment. And if you notice, he's not floating like boats float. He's actually sitting on top of the water. He's using that surface tension to hold himself up. If you were to like kill the bug and put him underwater, yeah, he would sink. He's not floating. He's sitting on top of the surface tension. So there's several types of bugs that will do that, and we'll try to do that in one of our activities. Another type of force between molecules is the force between different substances. So here we have water on glass, and if you've ever noticed after taking a shower, you get out of the shower and all the glass is covered with water, that water is clinging to the glass of your shower. with adhesive forces. Water will hold on tight to other things. That is the reason for, remember we talked about the meniscus when we were talking about graduated cylinders? The meniscus is that little, almost looks like a contact lens, because your water is clinging to the sides of the glass more strongly than to itself. So you end up having them pull up on either side and hold tight. That's adhesion. Think like adhesive stickers, that they're sticking to something. And finally, capillary action is a special type of adhesion. So adhesion is the main force here, but when you've got a tube where that adhesion is stronger than the cohesive force, especially the smaller diameter you get a little bit of capillary action with bigger containers, but the smaller that container gets, the more you get more adhesion on the outside than cohesion on the inside. So capillary action causes that water to actually raise up in the tube, and it doesn't have to be just glass. This is the way plants take in water through their roots. It's capillary action. The water clings to the sides of the roots and migrates upwards because they're wanting to adhere to the sides of the roots more than they're wanting to have cohesive forces with each other. And if you've ever had a blood sample taken like this, sometimes they'll do, if they're not doing a whole tube of blood, they'll just do a little tube like this of blood with a finger prick. There's no electronics here. There's no like vacuum motion. It's all, they're called capillary tubes. It's all capillary action where the blood is wanting to cling to the sides of the glass and move up in the tube more than it's wanting to cohere together. All right, so earlier when we were doing thermal energy, we talked about changing from a solid to a liquid and a liquid to a gas because of a change in thermal energy. But you don't have to have a change in thermal energy to change from a liquid to a vapor. The process is evaporation. And with evaporation, the particles that are on the surface of your liquid start moving fast enough that they eventually escape. They break free of those cohesive forces and become a vapor. And if you've set out water, then you've seen this happen. Your water will eventually evaporate because of those molecules on top going fast enough to leave. Now, when that happens, since you've got a molecule that was zipping around inside your liquid going fast and suddenly it's gone, it takes that thermal energy with it. So that kinetic energy is lost, the thermal energy is lost, and the liquid that's left over has a cooling effect. You notice it a little bit with water, but if you've ever had like you've scraped your knee and you put alcohol on your knee and then your mom blew on it, it wasn't just love and kisses to make your knee feel better. That alcohol has a very low evaporation point. It's a volatile liquid. Sorry, I forgot the word. It's a volatile liquid, meaning that it evaporates very easily, very quickly. And so you might have noticed that it got really cold on your little skint knee. So those liquids evaporate very easily and do have a great cooling effect there. On humid days, that evaporation is reduced. We don't have as much evaporation. So that's why we feel hotter, because if we were in a dry climate, that sweat that left our bodies would evaporate and cool us off. But since it's so humid, the water tends to stay on our skin, making us all sweaty and nasty and feeling terrible. So the flip side of that is condensation. When kinetic energy decreases, such as with this cold drink right here, then your particles that are in the air next to it slow down and condense back into a liquid. So the dew point, if you've ever watched the weather forecast and you've heard them talk about the dew point, that's the point at which the temperature gets low enough for the humidity in the air to condense back into a liquid and we get dew in the morning. So that is a temperature at which condensation will start to occur. So there's our properties of fluids. We will do some practice, some activities with this, and then we will be done with our properties of matter.